Imagine looking up at the night sky and realizing everything you see, every star, every galaxy, even the vast emptiness between them, is moving in a way that shouldn't be possible. Scientists call this phenomenon dark flow, and it's one of the most baffling mysteries in the cosmos. Picture the universe as a river with countless galaxies drifting together toward some unseen destination, pulled by a force so powerful it defies everything we know about physics. What could be out there beyond the edges of our observable universe, tugging at everything with such irresistible strength? This isn't science fiction, it's real. Dark flow challenges the very foundations of our understanding, suggesting there's something vast and unknown lurking in the shadows of space, something so immense it bends the fabric of reality itself. Think about that for a moment. We've mapped the cosmos, peered back billions of years to the birth of stars, even detected the faint echoes of the Big Bang. Yet here we are, staring at a mystery that refuses to fit into any equation, any theory. It's like watching a flock of birds suddenly change direction, not because of the wind, but because of something invisible, something beyond the horizon. And that's just the beginning. Over the next 30 facts, we're going to unravel the secrets of dark flow, exploring how it was discovered, what it might mean for the fate of the universe, and why some scientists believe it could rewrite the laws of physics as we know them. This is a journey into the unknown, a glimpse at the forces shaping reality on a scale so vast it's almost impossible to comprehend. So buckle up, because by the end of this, you'll never look at the night sky the same way again. In 2008, astronomers made a discovery that sent shockwaves through the scientific community, one that still challenges our understanding of the universe today. Using data from the Wilkinson Microwave Anisotropy Probe, or WMAP, researchers noticed something bizarre. Enormous clusters of galaxies, each containing thousands of stellar systems, were all moving in the same direction at speeds that defied explanation. It wasn't just a few galaxies drifting aimlessly. This was a coordinated motion, as if some unseen force were pulling them toward a single, mysterious point in space. Think about the scale of that for a second. Galaxies aren't just floating randomly, they're bound by gravity, shaped by the fabric of space-time itself. Yet here they were, breaking the rules, streaming toward some distant, invisible destination like iron filings drawn to a magnet. Scientists called this phenomenon dark flow, and it was unlike anything they'd ever observed. The implications were staggering. According to everything we know about cosmology, the universe should be expanding evenly in all directions after the Big Bang, with matter distributed more or less uniformly. But dark flow suggested something else. Something beyond our observable universe was exerting a gravitational pull so immense it could drag entire galaxy clusters off course. Some researchers even speculated it might be evidence of another universe, a parallel cosmos lurking just beyond the edge of our own, tugging at ours like a hidden neighbor pulling strings from the shadows. What made this discovery even more astonishing was how precise the measurements were. WMAP didn't just detect this motion, it mapped it with startling clarity, revealing that these galaxies weren't just drifting slightly. They were racing at speeds of nearly 1,000 kilometers per second toward something we couldn't see. That kind of motion doesn't happen by chance. It hints at forces we don't yet understand, at structures in the cosmos so vast they dwarf even the largest superclusters we've ever observed. For scientists, this was more than just a curiosity, it was a crisis. Dark flow didn't fit into the standard model of cosmology. It raised questions about what lies beyond the cosmic horizon, about whether our universe is truly alone, or if it's just one piece of a much larger, stranger puzzle. And that's why, even years later, dark flow remains one of the most tantalizing and unsettling mysteries in modern astronomy. To put dark flow's staggering speed into perspective, imagine this: entire galaxy clusters, each containing hundreds of billions of stars, are hurtling through space at nearly 1,000 kilometers per second. That's roughly 2.2 million miles per hour, a velocity so immense it could carry you from Earth to the Moon in under 7 minutes. Now compare that to our own planet's modest orbital speed around the Sun, a mere 30 kilometers per second. Earth feels like it's standing still next to this cosmic sprint. What makes these speeds so shocking isn't just the raw numbers, it's what they defy. The universe, as we understand it, should be expanding evenly in all directions, a gentle drift outward from the Big Bang's aftermath. Galaxies might have small, local movements like eddies in a river, but nothing like this coordinated, high-speed march toward some distant, invisible beacon. It's as if you dropped a handful of leaves into a calm pond, only to watch them all suddenly bolt in the same direction, ignoring the water's natural flow. Scientists first measured these velocities using the cosmic microwave background, the faint afterglow of the Big Bang. By studying subtle distortions in this primordial light, they could track how galaxy clusters were dragging space-time itself along with them, like boats leaving wakes in a cosmic sea. The findings were unmistakable. Something beyond our observable universe was pulling matter with gravitational force strong enough to override the universe's expansion. This isn't just a slight nudge we're talking about. At these speeds, a galaxy cluster could cross the entire Milky Way, 100,000 light-years wide, in just 100 million years. On cosmic timescales, that's a blink of an eye. Whatever's out there beyond the horizon of what we can see isn't just massive, it's exerting influence on scales that rewrite our understanding of gravity, structure, and perhaps even the nature of reality itself. The hunt for answers is far from over, but one thing's certain: dark flow is racing ahead, daring us to keep up. One of the most mind-bending aspects of dark flow isn't just its speed, it's the sheer scale over which this mysterious force operates. We're not talking about a few nearby galaxies swaying slightly off course. This phenomenon stretches across unimaginable distances, influencing galaxy clusters up to 3 billion light-years away from us. To put that into perspective, if you could travel at the speed of light, a feat impossible by our current understanding of physics, it would still take you 3 billion years just to reach the farthest reaches of dark flow's grip. That's older than Earth itself by nearly 2 billion years. This cosmic current challenges one of astronomy's most fundamental assumptions, the cosmological principle. For centuries, scientists have operated under the idea that the universe is homogeneous and isotropic, meaning it should look roughly the same in all directions, with matter evenly distributed on the largest scales. But dark flow throws a wrench into that theory. How could the universe appear uniform if vast swaths of it are being dragged in the same direction by something we can't even see? It's like standing in what you thought was a perfectly still lake, only to realize the entire body of water is secretly flowing toward some hidden drain. What makes this even more puzzling is that 3 billion light-years marks the very edge of what we can observe. Beyond that point, the expansion of the universe carries galaxies away faster than light can reach us, rendering them invisible to our telescopes. So if dark flow's influence extends that far and possibly even farther, it implies whatever's causing it lies beyond our cosmic horizon, in realms we may never directly observe. Some theorists suggest this could be evidence of a supermassive structure, perhaps a concentration of matter so colossal it defies comprehension, lurking in the unobservable universe. Others speculate it might be the gravitational fingerprint of another universe entirely, one brushing against ours in ways we're only beginning to detect. The implications ripple through everything we thought we knew. If the cosmological principle doesn't hold at these scales, it could mean our universe isn't the smooth, evenly distributed expanse we've long imagined. There might be wrinkles in the fabric of space-time, cosmic undercurrents and tides shaped by forces we've yet to name. Dark flow doesn't just hint at hidden structures. It suggests the universe is far stranger, far more dynamic than our textbooks ever dared to propose. And that realization is what keeps astronomers staring at their data, searching for clues in the dark. Now, let's clear up a common point of confusion. Dark flow isn't the same as dark matter or dark energy, even though they all share that eerie dark label. These cosmic mysteries operate on entirely different scales and principles, each revealing a unique piece of the universe's puzzle. Dark matter, for instance, acts like invisible scaffolding, holding galaxies together with its gravitational pull. We can't see it, but we know it's there because without it, galaxies would fly apart. Dark energy, on the other hand, is the mysterious force accelerating the universe's expansion, pushing galaxies apart faster and faster over time. But dark flow, it's something else entirely. While dark matter and dark energy work within our observable universe, dark flow suggests an influence from beyond it. Imagine dark matter as the glue inside a snow globe, keeping everything in place, and dark energy as the hand shaking that globe, making the flakes inside drift apart. Dark flow, though, would be like someone tilting the entire snow globe sideways, sending all those flakes sliding in one direction, even though nothing inside the globe is causing that tilt. That's the key difference. Dark flow isn't just about what's in the universe, it's about something outside tugging on it. Scientists have checked repeatedly. They've mapped the distribution of dark matter, calculated the effects of dark energy, and run simulations to see if these forces could explain the coordinated motion of galaxy clusters. The answer, no. The pull of dark flow is too strong, too uniform, and too focused to be the work of dark matter's scattered influence or dark energy's broad push. It's as if you were floating in a river and suddenly the current didn't just speed up, it dragged you sideways toward a waterfall no one else could see. This distinction is what makes dark flow so revolutionary. Dark matter and dark energy fit within our current models, uncomfortable as they may be, but dark flow. It hints at forces or structures beyond those models, beyond even the edges of our cosmic map. If dark matter is the hidden skeleton of the universe and dark energy its invisible engine, then dark flow might be the shadow of something or somewhere we've yet to discover. And that's a mystery that keeps physicists awake at night. The Great Attractor, it sounds like something straight out of a sci-fi epic, but this colossal gravitational anomaly is very real, lurking about 250 million light-years away in the direction of the Centaurus and Hydra constellations. For decades, astronomers have known something massive is pulling our Milky Way and thousands of other galaxies toward it at breakneck speeds. At first glance, it seems like the perfect suspect behind dark flow's mysterious tug. But here's the twist. The Great Attractor, as powerful as it is, can't possibly explain the full scale of this cosmic drift. Think of it like this. If dark flow were a river sweeping entire galaxy clusters downstream, the Great Attractor might be a boulder creating a local ripple, but it's nowhere near strong enough to account for the river's entire current. Measurements show the Great Attractor's gravity is immense, sure, but its influence fades dramatically over distance. Meanwhile, dark flow's pull remains relentless across billions of light-years, far beyond where the attractor's grip should reach. It's like trying to blame a neighborhood magnet for shifting the course of every compass on Earth. The scales just don't match up. There's another clue that points to something even bigger at play. The Great Attractor sits within our observable universe. Its mass detectable through the way it bends light and distorts the motion of nearby galaxies. But dark flow's source appears to lie beyond what we can see, in regions of space so distant their light hasn't had time to reach us since the Big Bang. That means whatever's pulling on these galaxy clusters isn't just massive, it's outside our cosmic horizon, hidden behind the veil of time itself. So while the Great Attractor remains one of the universe's most fascinating puzzles, it's merely a piece of a far larger mystery. Some scientists speculate that dark flow could be the combined effect of multiple such anomalies, a cosmic chain of gravitational giants we've yet to map. Others wonder if the attractor itself is being pulled by something even more enormous, like a fish caught in a current it didn't create. One thing's certain: until we unravel what lies beyond the edges of our observable universe, dark flow will keep dragging us and our theories into uncharted territory. If the universe were a cosmic ocean, supervoids would be its emptiest stretches, vast regions where galaxies are few and far between. These enormous bubbles of near-nothingness, some spanning hundreds of millions of light-years, aren't just blank spaces. They exert their own peculiar pull on the fabric of the cosmos. Here's how it works. When a galaxy cluster approaches the edge of a supervoid, the lack of mass inside creates a kind of gravitational imbalance, subtly nudging the cluster away from the void's center. Scientists call this the repeller effect, as if these voids are gently pushing matter toward denser regions of the universe. At first glance, this seems like a promising clue to unravel dark flow's mystery. Could these repeller regions be the invisible hands guiding galaxy clusters in their strange, synchronized march? The answer, frustratingly, is no, at least not entirely. While supervoids do influence the motion of nearby galaxies, their push is far too feeble to account for the jaw-dropping speeds and coherence of dark flow. Picture trying to steer a cruise ship with a desk fan. The fan might create a breeze, but it's nowhere near powerful enough to set the entire vessel on a new course across the ocean. The numbers don't add up either. Even the largest known supervoids, like the Eridanus supervoid, a staggering 1 billion light-years across, only generate a fraction of the gravitational effect needed to explain dark flow's relentless pull. Worse yet, these voids are scattered randomly across the cosmos, while dark flow points galaxy clusters in one specific direction. It's as if every leaf in a forest was blowing east, but the wind you feel is coming from all directions at once. That doesn't mean supervoids aren't fascinating in their own right. These cosmic deserts challenge our assumptions about how matter is distributed, revealing a universe that's lumpier and less uniform than we once thought. Some researchers even speculate they could be echoes of primordial fluctuations, scars from the universe's violent infancy. But when it comes to dark flow, they're more like red herrings, tantalizing distractions from a deeper, darker enigma. So if it's not supervoids and it's not the Great Attractor, what's left? The unsettling truth is that dark flow's origin might lie beyond the reach of our telescopes, in realms where the familiar rules of physics no longer apply. Some theories suggest these repeller regions could be part of a larger, unseen structure, a cosmic skeleton we've only begun to trace. Others wonder if we're seeing the gravitational shadow of another universe entirely, one brushing against ours in ways we can't yet comprehend. Whatever the answer, one thing's clear: the universe is playing a game of tug-of-war, and we're only just starting to glimpse the ropes. Scientists searching for the origins of dark flow turn to the oldest light in the universe, the cosmic microwave background. This faint glow, lingering from the Big Bang itself, serves as a cosmic fossil, preserving patterns from when the universe was just 380,000 years old. Normally, this radiation appears nearly uniform in all directions, like static on an old television screen. But when researchers analyzed data from space telescopes like WMAP and Planck, they spotted something peculiar: a subtle but unmistakable tilt in the CMB's temperature, aligned perfectly with the direction of dark flow's mysterious pull. Imagine blowing across the surface of a steaming cup of coffee, watching the ripples shift in one direction. That's essentially what astronomers were seeing, except instead of steam, they were observing the afterglow of creation, and instead of breath, some unseen force was nudging it sideways. This tilt, technically called the kinematic dipole, shouldn't exist if the universe were expanding evenly in all directions. Yet there it was, a telltale fingerprint in the primordial light, suggesting vast swaths of matter were on the move. Here's why this discovery was groundbreaking. The cosmic microwave background is our most reliable map of the early universe. Its patterns reveal how matter was distributed just after the Big Bang, like a snapshot of cosmic infancy. Normally, any motion in the universe, like our solar system orbiting the Milky Way, creates a predictable Doppler shift in the CMB, much like how an ambulance's siren sounds different as it passes by. But dark flow's signature was different. The temperature variations were too large, too coordinated, and they pointed towards something outside our observable universe. It was as if every galaxy cluster was rowing in sync toward some distant, invisible shore, leaving wakes in the fabric of spacetime itself. Critics initially argued this could just be an illusion, perhaps an error in data calibration or an overlooked local effect. But as measurements grew more precise, the evidence only solidified. The tilt wasn't random noise. It matched exactly with the motion of galaxy clusters millions of light-years apart. Even more startling, the scale of this alignment suggested the source of dark flow's pull must lie beyond the cosmic horizon, in regions of space we'll never see directly. What does this mean for our understanding of the cosmos? The CMB tilt isn't just a curiosity, it's a cosmic breadcrumb, hinting at forces or structures so vast they defy our current models. Some theorists speculate these irregularities could be echoes of quantum fluctuations from the universe's first moments, magnified to unimaginable scales. Others wonder if we're seeing the gravitational shadow of another universe, one that brushed against ours in the distant past. Whatever the explanation, one thing's clear: the oldest light in the universe is telling us a story we're only beginning to decipher, and dark flow is its most tantalizing chapter. The Big Bang theory rests on a fundamental assumption, the cosmological principle, which states that on the largest scales, the universe should look roughly the same in all directions. Matter, energy, and the very fabric of spacetime should be evenly distributed, like frosting spread smoothly across a cosmic cake. This idea isn't just a hunch, it's the backbone of modern cosmology, explaining everything from the cosmic microwave background to the way galaxies cluster together. But dark flow throws a wrench into this elegant picture, revealing what appears to be a colossal asymmetry, a universe that's not uniform at all, but pulled in one specific direction by something unseen. Imagine blowing up a balloon covered in tiny dots. As the balloon expands, every dot should move away from every other dot equally, maintaining a symmetrical, uniform pattern. That's how the Big Bang model describes cosmic expansion. But dark flow suggests some dots aren't just drifting apart, they're also sliding sideways, as if an invisible finger were pressing against the balloon's surface. This isn't a small deviation, it's a direct challenge to the idea that the universe is homogeneous. If vast swaths of matter are streaming toward a single point, it implies there's a preferred direction in the cosmos, a notion that clashes head-on with the Big Bang's foundational assumptions. The implications ripple far beyond theoretical debates. If the universe isn't uniform, it could mean our understanding of its origins is incomplete, or even fundamentally flawed. The Big Bang's predictions about the distribution of galaxies, the behavior of dark energy, and the ultimate fate of the cosmos all rely on that smooth, even starting point. Remove that assumption, and suddenly, the equations that describe the universe's evolution might need rewriting. Some scientists argue dark flow could hint at exotic physics, like variations in the strength of gravity over cosmic distances or hidden dimensions tugging at our reality. Others propose a more radical idea, that what we call the Big Bang wasn't the only one, and our universe is just one bubble in a frothing multiverse, jostled by the gravity of its unseen neighbors. This isn't just academic speculation. If dark flow's pull is real, it means there are structures or forces beyond our cosmic horizon so massive they distort the universe on scales we once thought impossible. Picture a river flowing silently in the dark, until one day you realize its current isn't random. Something vast and unseen is steering it. That's the dilemma cosmologists face. Do they tweak the Big Bang model to accommodate this anomaly, or do they search for a whole new framework to explain a universe that's far stranger, far less uniform than we ever imagined? The answers, much like the source of dark flow itself, remain just out of reach. Dark flow's mystery has sparked some of the most daring theories in modern cosmology, ideas so radical they sound like they're ripped from the pages of a science fiction novel. One leading hypothesis suggests the pull we're observing could come from a neighboring universe, a parallel cosmos brushing against ours like ships passing in the night. Picture two soap bubbles floating close together, their surfaces briefly touching. If another universe existed just beyond the edge of our own, its gravity might seep through, tugging at galaxy clusters like a phantom hand. This isn't just wild speculation, it's grounded in the mathematics of string theory and the multiverse concept, where higher dimensions could allow gravitational forces to leak between realities we can't otherwise perceive. Then there's the idea of a pre-Big Bang structure, remnants of something that existed before our universe began. If the Big Bang wasn't the absolute start but rather a phase transition, like water freezing into ice, then remnants of an earlier epoch might still linger beyond our cosmic horizon. These ancient gravitational scars imprinted on spacetime itself could be warping the motion of galaxies even now. It's like finding a footprint in dried concrete and realizing it was made by a shoe no one's ever seen. Not all theories are quite so exotic. Some physicists propose simpler, if still unsettling, explanations. Perhaps our measurements are flawed or we're misinterpreting the data. After all, dark flow's signal is faint, buried in noise at the edge of detectability. But each time researchers double-check using newer telescopes, sharper algorithms, the anomaly persists. Others suggest undiscovered physics, like modifications to Einstein's theory of gravity, that would allow distant masses to exert stronger pulls than expected. Yet even these tweaks struggle to explain the sheer scale of dark flow's coordination across billions of light years. The most compelling part, these aren't mutually exclusive ideas. The truth might lie in a combination, some blend of multiverse gravity, primordial structures, and laws we haven't yet written. What's certain is that dark flow refuses to fit neatly into any existing box. It's a cosmic riddle demanding we rethink not just what's in the universe, but what, or who else might be out there. Galaxy clusters aren't just cosmic landmarks, they're the universe's most sensitive scales, capable of weighing even the faintest gravitational tugs. Each one is a sprawling metropolis of hundreds or even thousands of galaxies, bound together by gravity over billions of years. Their sheer size is what makes them perfect for detecting dark flow's subtle pull. Picture trying to measure a gentle breeze. A single leaf might flutter unpredictably, but an entire forest bends in unison, revealing the wind's true direction. Galaxy clusters work the same way. Individual galaxies dart around too much to trace precise motions, but when you track a cluster, a behemoth weighing a quadrillion times more than our Sun, its movement becomes a clear arrow pointing toward whatever's pulling it. What's fascinating is how slowly these giants drift. Unlike stars or small galaxies, which can zip around at high speeds, galaxy clusters move through the cosmos with a stately, almost sluggish pace. That slowness is key. Imagine watching two snails crawl across a sidewalk. Their tiny, deliberate steps make it easy to spot if one starts veering off course. Dark flow's influence is equally subtle, nudging clusters just slightly off the expected path of cosmic expansion. But because these clusters are so massive and slow, that tiny deviation stands out like a fingerprint on glass. Scientists measure this motion using a clever trick involving the cosmic microwave background. As galaxy clusters drift, their immense gravity distorts the CMB's light in a predictable way, creating a shadow effect known as the Sunyaev-Zeldovich effect. By studying these shadows across hundreds of clusters, researchers can map their collective motion with astonishing precision. The results are unmistakable. entire clusters separated by hundreds of millions of light years are all being dragged in the same direction, like iron filings aligning to a magnet hidden just beneath the table. This method has another advantage. It sidesteps the murky problem of distance measurements. Normally, calculating how fast something moves in space requires knowing exactly how far away it is, a tricky task in astronomy. But with galaxy clusters and the CMB, scientists can measure motion without needing precise distances, cutting through one of cosmology's biggest uncertainties. It's like judging a river's current by watching how floating debris moves rather than trying to guess each twig's exact position. The implications go beyond dark flow. By studying how these clusters respond to unseen forces, we're essentially turning them into cosmic probes, mapping the gravitational landscape of the universe in ways no telescope could. Every deviation, every slight shift in their path is a clue, a whisper from the dark, hinting at structures or phenomena we've yet to imagine. And that's what makes galaxy clusters more than just celestial curiosities. They're our guides into the unknown, massive enough to feel the universe's faintest tremors and patient enough to let us read them. When the Planck satellite launched in 2009, scientists hoped its ultra-precise measurements of the cosmic microwave background would finally solve the dark flow mystery once and for all. This advanced European Space Agency mission carried instruments 10 times more sensitive than WMAP, capable of detecting temperature variations in the CMB down to millionths of a degree. If dark flow was real, Planck should have spotted it with crystal clarity, but what it actually found sent researchers back to the drawing board. At first glance, Planck's data seemed to confirm WMAP's earlier detection of galaxy clusters moving in unison. The satellite's painstaking measurements showed the same subtle temperature shifts in the CMB, aligned with that puzzling flow direction. But when scientists dug deeper, inconsistencies emerged. Planck's numbers suggested the effect might be weaker than WMAP had indicated, with some galaxy clusters appearing to resist the flow entirely. It was like two teams using different scales to weigh the same object. Both agreed it had mass, but they couldn't settle on exactly how much. The discrepancies forced astronomers to confront uncomfortable possibilities. Maybe WMAP had overestimated dark flow's strength due to unforeseen calibration issues or interference from our own Milky Way's motion. Or perhaps Planck's improved sensitivity revealed complexities WMAP simply couldn't see, like discovering your straight garden path actually has subtle curves only visible under a magnifying glass. Some researchers even proposed that dark flow might not be a single, uniform current, but rather a patchwork of regional flows, some strong and some weak, creating a misleading impression when viewed from Earth. Most confusing of all was Planck's measurement of the cosmic dipole, that telltale temperature tilt in the CMB that aligns with dark flow's direction. While Planck broadly agreed with WMAP dipole detection, the satellite's sharper vision revealed unexpected small-scale variations that didn't fit neatly into existing models. These fluctuations hinted that whatever's causing dark flow might be more nuanced than a simple gravitational pull from beyond our horizon. Imagine tracking a herd of deer moving together and suddenly noticing some animals occasionally break formation, still heading the same general way, but with individual detours that complicate the pattern. The Planck results didn't disprove dark flow, but they transformed the debate. Instead of a clear yes or no question, scientists now faced a spectrum of maybes. Could the flow be real but intermittent, its signal waxing and waning across different regions of space? Might it interact with unknown large-scale structures in ways we don't yet understand? Or was Planck's superior data revealing that our entire concept of dark flow needed rethinking, not as a single mysterious force, but as the combined effect of multiple cosmic phenomena we're only beginning to untangle? What makes Planck's findings so valuable isn't just their precision, it's their stubborn refusal to give easy answers. By confirming parts of the dark flow signal while muddying others, the satellite forced cosmology to grow more sophisticated in its questions. Sometimes the most powerful scientific instruments don't solve mysteries, they reveal how much deeper those mysteries go. And that's exactly what Planck did, leaving us with a universe more puzzling, more intriguing than we'd ever imagined. Not every scientist is convinced dark flow is real, and their skepticism isn't just stubbornness. Some researchers argue the entire phenomenon could be an illusion, a cosmic mirage created by subtle errors in how we measure the universe's vast distances and motions. One major critique focuses on something called galaxy cluster catalog contamination. Imagine trying to track the migration patterns of birds, but some of the birds in your study aren't actually flying. They're just leaves blown by the wind. That's essentially the worry here. If even a small percentage of the galaxy clusters used to detect dark flow are misidentified or aren't true clusters at all, their apparent motion could skew the entire dataset, creating a false signal where none exists. Others point to the challenge of distinguishing dark flow from our own local motion. Earth orbits the Sun, which orbits the Milky Way, which itself is moving through the local group of galaxies, all while being tugged toward the Great Attractor. These overlapping movements create a complex foreground, noise, that could mimic or amplify a larger scale flow. Think of standing on a train and trying to judge whether the platform outside is moving while your own carriage sways slightly. Without perfect calibration, separating real cosmic motion from these local effects is nearly impossible, and critics argue current measurements might not be precise enough to tell the difference. Then there's the statistical argument. With billions of galaxies in the observable universe, some clusters are bound to move in similar directions purely by chance, like flipping a coin enough times that you eventually get 10 heads in a row. Skeptics suggest dark flow might just be one of these random alignments, a temporary coincidence that looks meaningful simply because we're seeing a snapshot of an ever-changing cosmos. After all, if you zoom out far enough, even the most chaotic systems can appear orderly for a moment, like watching a crowd at a stadium and noticing a brief, accidental wave that wasn't actually started by anyone. The most damning critique comes from studies using alternative methods. While the cosmic microwave background technique initially supported dark flow, other approaches like tracking the motions of supernova or using different galaxy cluster catalogs have failed to consistently replicate the effect. It's as if one medical test shows you have a rare condition, but 5 others come back clean. Which result do you trust? In science, extraordinary claims require extraordinary evidence, and some argue dark flow hasn't yet met that burden. But here's where it gets interesting. Even critics admit the debate isn't settled. Newer telescopes and analytical techniques keep refining our measurements, and with each upgrade, the signal either weakens or stubbornly persists. That's how science moves forward, not by unanimous agreement, but through relentless questioning, testing, and revising. Whether dark flow ultimately proves real or not, the controversy itself has already reshaped how we study the universe's largest structures, reminding us that even our best tools have limits, and that the cosmos always keeps a few secrets in reserve. Astronomers have been locked in an increasingly heated debate over the Hubble constant, the number that tells us how fast the universe is expanding. On one side, measurements using nearby galaxies and supernova suggest a relatively rapid expansion rate. On the other, observations of the cosmic microwave background point to a slower, more gradual pace. The discrepancy isn't small. It's a full-blown crisis in cosmology, with each method stubbornly disagreeing by nearly 10%. This isn't just academic nitpicking, it's like 2 clocks telling different times, and the deeper we look, the more we realize one of them might be fundamentally broken. Enter dark flow. Some theorists speculate this mysterious cosmic current could be the missing piece in the Hubble constant puzzle. If vast regions of the universe are being tugged by unseen forces, those motions might be subtly distorting our measurements of cosmic expansion. Imagine trying to measure the speed of a river while unknowingly standing on a raft being pulled by an underwater current. Your readings would be off, not because the river itself is changing, but because hidden forces are interfering with your perspective. Dark flow could be doing something similar on a galactic scale, skewing our local measurements of the Hubble constant without us realizing it. The connection gets even more intriguing when you consider the cosmic microwave background. The same primordial light that gives us one value for the Hubble constant also carries the fingerprints of dark flow's influence. If dark flow's pull is real, it might mean the CMB isn't the pristine, undisturbed record we thought it was, that its light has been slightly warped by the motion of galaxy clusters over billions of years. That distortion could be throwing off our calculations, explaining why the CMB-derived Hubble constant disagrees so sharply with other methods. It's like trying to read a book while someone jostles your arm. The words are still there, but their meaning gets blurred. Not everyone is convinced, of course. Critics argue that dark flow's influence, even if real, wouldn't be nearly strong enough to account for the Hubble tension. But the mere possibility has opened a new frontier in cosmology. Instead of treating the Hubble constant discrepancy as a problem with our measurements, some scientists are now asking, what if it's a clue? A sign that our universe isn't as uniform as we assumed, that hidden currents and unseen structures are subtly reshaping reality on scales we're only beginning to perceive. If true, it would mean dark flow isn't just a curiosity, it's a key to unlocking one of the biggest mysteries in modern astrophysics. The stakes couldn't be higher. Resolving the Hubble tension isn't just about pinning down a number, it's about understanding the fate of the cosmos itself. Is the universe expanding fast enough to eventually tear galaxies apart? Or is dark energy weaker than we thought, leaving room for a slower, more measured end? Dark flow's role in this drama is still uncertain, but one thing's clear. The universe is sending us mixed signals, and deciphering them might require rewriting the rules of cosmology itself. What if our universe isn't alone? The eerie, unexplained motion of dark flow has led some scientists to consider a possibility straight out of theoretical physics, that we're feeling the gravitational whisper of another universe entirely. Picture two soap bubbles floating side by side, nearly touching but not quite. If another cosmos exists just beyond the edge of our own, its gravity could subtly warp our universe's fabric, tugging galaxy clusters like a magnet under a sheet of paper. This isn't just wild speculation. It's rooted in serious theories like the multiverse and brain cosmology, which suggest our reality might be one of many, each with its own physics, its own laws, its own hidden pull. The math behind this idea is both elegant and unsettling. In string theory, our universe could be a three-dimensional brain floating in a higher dimensional space, like a page in a vast cosmic book. Other brains, other universes might drift nearby, separated by dimensions we can't perceive. Normally, these brains wouldn't interact, but if they occasionally brushed against each other, even faintly, the gravitational disturbance could ripple through our cosmos, nudging everything in one direction. Dark flow's coordinated motion matches exactly what you'd expect from such an encounter, like feeling the breeze from a door opening in a room you thought was sealed shut. Critics argue this explanation leans too heavily on untestable ideas, but here's where dark flow gets even stranger. The flow's direction points toward a region of space with no known massive structures, no superclusters, no Great Attractor, nothing that could explain the pull through conventional physics. It's as if you dropped a marble on a table and watched it roll steadily toward the edge despite the surface being perfectly level. Where is it going? What's pulling it? The unsettling answer might be something off the table entirely. Of course, the multiverse isn't the only possible explanation. Some researchers propose dark flow could be evidence of a cosmic defect, a flaw in space-time left over from the universe's birth, like a crack in frozen ice. These defects, predicted by some grand unified theories, could create vast gravitational anomalies that warp the motion of galaxies. Others wonder if we're seeing the remnants of a long-ago collision between our universe and another, a cosmic fender bender that left everything slightly off-kilter. But the multiverse hypothesis lingers because it answers two questions at once. What's pulling us, and why can't we see it? If the source of dark flow lies outside our observable universe, it would explain why our telescopes show nothing in that direction, and why the pull persists across billions of light years without weakening. It's like hearing an echo in a cave and realizing the sound isn't bouncing off the walls you can see, but from a chamber hidden deeper in the mountain. The implications are dizzying. If dark flow truly is evidence of another universe, it would mean we're not just mapping the cosmos, we're glimpsing what lies beyond it. Not with telescopes or probes, but through the silent, insistent tug of gravity, a force that might transcend the boundaries of reality itself. For now, the idea remains speculative, a thrilling possibility hovering at the edge of proof. But if future observations keep pointing in the same direction, we might have to confront a truth as profound as any in science, that our universe is just one ripple in an ocean of realities, each pulling, pushing, and shaping the others in ways we're only beginning to sense. The mystery of dark flow may soon meet its match cutting-edge telescopes and space missions designed to peer deeper into the cosmos than ever before. Leading the charge is the European Space Agency's Euclid telescope, launched in 2023 with one audacious goal: to map the invisible skeleton of the universe. Unlike traditional telescopes that focus on stars and galaxies, Euclid specializes in detecting dark matter's gravitational fingerprints and tracing dark energy's influence across 10 billion light-years of space. But here's where it gets exciting for dark flow researchers. Euclid's razor-sharp optics and wide-field surveys could finally distinguish whether galaxy clusters are moving due to unseen mass within our universe, or something far more exotic lurking beyond it. Then there's NASA's upcoming Nancy Grace Roman Space Telescope, set to launch by 2027. Dubbed the Mother of Hubble, this instrument will survey the sky with a field of view 100 times wider than Hubble's, capturing the motions of millions of galaxies in unprecedented detail. Roman's infrared vision cuts through cosmic dust like night vision goggles, revealing subtle distortions in spacetime that might betray dark flow's source. Imagine trying to solve a jigsaw puzzle with half the pieces missing. Roman's vast datasets could supply the missing fragments, showing whether the flow connects to known structures or points toward uncharted territory. Ground-based observatories aren't sitting idle either. The Vera C. Rubin Observatory, perched in Chile's arid mountains, will soon begin the legacy survey of space and time, a decade-long movie of the southern sky capturing celestial motions frame by frame. With its 3.2 billion pixel camera, Rubin could spot tiny deviations in galaxy cluster trajectories, measuring dark flow's strength with pixel-perfect precision. Combine that with the square-kilometer array, a sprawling radio telescope network now under construction across 2 continents, and scientists will soon have multiple independent ways to verify whether dark flow is real or a cosmic mirage. But perhaps the most revolutionary tool isn't a telescope at all. Next-generation gravitational wave detectors, like the proposed Laser Interferometer Space Antenna, or LISA, could sense ripples in spacetime from colossal events we can't yet see, collisions between supermassive black holes, or even the gravitational echoes of other universes brushing against ours. If dark flow stems from such unseen cataclysms, LISA ultra-sensitive antennas might pick up their vibrations like a stethoscope listening to the universe's heartbeat. The stakes couldn't be higher. Each of these missions approaches the puzzle from a different angle: Euclid mapping dark matter's distribution, Roman tracking galaxy motions, Rubin monitoring cosmic drift, and LISA eavesdropping on spacetime itself. If their findings converge, we might finally learn whether dark flow is a flaw in our models, a shadow from beyond our cosmic horizon, or something even more extraordinary? One thing's certain, the next decade of astronomy won't just study the universe we know, it'll probe the edges of what we don't, and dark flow's enigma is first in line for answers. The universe isn't just a random scattering of galaxies, it's a vast, intricate network of filaments and voids known as the cosmic web. Picture it like a spider's silk stretching across the darkness, with galaxies clustered along its shimmering threads, separated by immense, empty bubbles. This delicate structure isn't just a cosmic backdrop, it's a dynamic highway system shaping how matter moves across the universe, and dark flow might be riding its currents like a surfer catching a wave. Here's how it works. The cosmic web's filaments are made of dark matter, that invisible scaffolding that holds galaxies together. Their gravity doesn't just anchor galaxies, it funnels them along specific paths like water flowing through a canyon. Scientists suspect these filaments could act as cosmic amplifiers, taking the faint tug of dark flow and magnifying it across unfathomable distances. Imagine whispering into one end of a taut string and having the sound emerge louder at the other end. The cosmic web might be doing something similar with gravity, transmitting dark flow's pull more efficiently than empty space ever could. But there's a twist. The web's structure isn't uniform. Some regions are dense, with multiple filaments braiding together into superhighways of matter. Others are sparse, with gravity's grip weakened by vast voids. This unevenness could explain why dark flow isn't perfectly smooth, why some galaxy clusters seem to move faster or slower than others. It's like wind passing through a forest. Where the trees grow thick, the air slows and eddies. Where they thin out, the gusts rush unimpeded. The cosmic web's tangled architecture might be sculpting dark flow's current in ways we're only beginning to map. What's truly fascinating is how this interplay could solve another puzzle: why dark flow's direction doesn't quite align with any known supercluster or void. If the cosmic web's filaments are redirecting the flow, then the source of this mysterious pull might not lie in a straight line from Earth. Instead, gravity's invisible threads could be bending the signal like a lens warping light. Think of it as trying to trace a river's origin by following its twists and turns. What looks like a straight path might actually be a winding journey through the cosmic landscape. This idea isn't just theoretical. Supercomputer simulations show how the cosmic web channels matter on colossal scales, with galaxies sliding along filaments like beads on a string. Some models even suggest these structures might funnel dark flow's influence toward specific regions, creating hotspots in the universe's gravitational field. It's a bit like how ocean currents can steer heat across the planet, creating warm patches thousands of miles from their source. If the cosmic web really is shaping dark flow, then hidden hubs of gravity, places we haven't even discovered yet, could be pulling the strings behind the scenes. Yet for all its promise, this theory raises new questions. How much of dark flow is truly coming from beyond our universe, and how much is the cosmic web's own motion? Could some clusters be drifting because of local filament dynamics rather than a grand, mysterious pull? Untangling this cosmic knot will take more than simulations. It'll require sharper observations, better maps of the web's furthest reaches, and perhaps a whole new way of thinking about how gravity weaves the universe together. One thing's certain: the cosmic web isn't just a stage for dark flow. It might be the unseen hand guiding its every move. If you traced the path of dark flow across the night sky, you'd find all those drifting galaxy clusters pointing toward a seemingly unremarkable patch of space near the constellations Centaurus and Hydra. At first glance, there's nothing particularly special about this direction. No blinding quasars, no sprawling superclusters, just an ordinary stretch of cosmic real estate. But that's exactly what makes it so baffling. If something out there is strong enough to haul entire galaxy clusters off course, why can't we see anything at the destination? This mystery only deepens when you examine the region closely. Telescopes have scoured this part of the sky, searching for any sign of a gravitational heavyweight, a supercluster of unprecedented size, a black hole of unimaginable mass, something that could justify the relentless pull. Yet every scan comes up empty. The area appears no denser than any other random slice of the universe, defying the basic rule that gravity comes from mass. It's like following a compass needle to what should be a mountain, only to arrive at flat, empty desert. Even stranger is the alignment. The Centaurus-Hydra direction doesn't match up with any known large-scale structures, like the Shapley supercluster, one of the most massive concentrations of matter we've found, which sits off to the side of dark flow's path. If Shapley's gravity were responsible, we'd expect the flow to angle toward it, not past it. Instead, dark flow's trajectory seems to ignore local attractors entirely, as if locked onto a target far beyond our observational limits. Some researchers compare it to a ship steering not by nearby lighthouses, but by stars invisible to the naked eye. Theories abound to explain this cosmic blind spot. One possibility is that the source lies so far away beyond the cosmic horizon that its light hasn't had time to reach us since the Big Bang. Another suggests it could be a structure so ancient it formed before the first stars ignited, leaving no visible trace in the night sky. The most radical idea, that we're seeing the gravitational echo of a pre-Big Bang anomaly, a scar in space-time from an era before our universe began. Whatever the truth, one thing's clear. Dark flow's empty target isn't just a puzzle, it's a glaring clue that our cosmic map is missing something monumental. What makes this direction even more unsettling is its persistence. Galaxies 3 billion light-years apart all seem to stream toward the same point, as if drawn by some unseen conductor's baton. In a universe where matter is supposed to be evenly distributed, such perfect alignment shouldn't exist. It's the astronomical equivalent of throwing 100 marbles into the air and watching them all curve toward a single spot on the floor, against all odds, against all physics. Until we uncover what's lurking in that dark corner of Centaurus and Hydra, dark flow will remain a ghostly finger pointing toward answers we can't yet see. The math just doesn't add up. No single structure we've discovered in the observable universe has enough mass to explain dark flow's relentless pull. Take the Shapley supercluster, for instance. It's the most massive concentration of galaxies we've ever found, weighing in at roughly 10,000 times the mass of the Milky Way, a titan by any measure, right? Yet even this cosmic behemoth can't account for the sheer scale of dark flow's influence. The force required to drag galaxy clusters across billions of light-years would demand something 100 times more massive than Shapley, a structure so enormous it would dominate our sky, eclipsing everything else. And here's the kicker: if something like that existed within our observable universe, we'd have seen it by now. Our telescopes would have spotted its gravitational lensing effects, its telltale distortions of space-time. But the sky in dark flow's direction remains stubbornly ordinary. It's not just about raw mass either. Gravity weakens with distance, a fundamental rule we've known since Newton. For a supercluster to yank galaxies billions of light-years away, its gravitational pull would need to defy this inverse square law, maintaining freakish strength across cosmic distances. That's like trying to move a parked car by blowing on it from a mile away. Even the most optimistic calculations show that known structures, whether the Great Attractor, the Pisces-Perseus supercluster, or any other contender, lose their grip long before reaching the scales where dark flow operates. Their influence simply fades into background noise, leaving no trace of the coordinated motion we observe. There's an even deeper puzzle here. If some unseen mega-structure were tugging on galaxy clusters, it wouldn't just affect their motion. It would warp the very fabric of space-time around it, bending light in ways we could detect. Astronomers have searched for these distortions, mapping the cosmic microwave background and the large-scale distribution of galaxies for any hint of a hidden gravitational giant. The result, nothing. No ghostly silhouette of a supermassive attractor, no telltale warping of the cosmic web. Just empty space where our models insist something colossal should be. This leaves us with two unsettling possibilities. Either there's a flaw in our understanding of gravity itself, some exotic physics that amplifies weak pulls across cosmic distances, or dark flow's source isn't in our universe at all. The first option would upend Einstein's theory of general relativity, forcing us to rewrite the rules that have guided cosmology for a century. The second, well, that opens the door to something even stranger, a gravitational whisper from beyond the edge of reality, a place our telescopes can never see. For now, the mystery stands as a monument to the limits of human knowledge. We've scoured the skies, weighed the galaxies, and traced the threads of the cosmic web, yet dark flow's puppet master remains hidden, pulling strings from the shadows. Whatever's out there, it's not playing by the rules we know, and that's what makes this cosmic whodunit so thrilling. The answer, when it comes, might not just solve dark flow's riddle, it could redefine our place in the universe. Could the ghostly tug of dark flow trace its origins to the universe's earliest moments, to quantum fluctuations so tiny they defy comprehension? At the subatomic scale, particles flicker in and out of existence like static on a cosmic radio, their fleeting energy bending the fabric of spacetime itself. These quantum jitters, amplified by the hyper-expansion of the Big Bang, are already known to have sculpted the universe's largest structures, galaxies, superclusters, and the cosmic web. But what if they also left behind deeper scars, anomalies in gravity powerful enough to steer entire galaxy clusters billions of years later? The idea isn't as far-fetched as it sounds. According to inflation theory, microscopic quantum ripples in the newborn universe were stretched to cosmic proportions during its rapid expansion, becoming the seeds for all future structure. Most of these fluctuations evened out over time, but some might have grown into gravitational lumps, regions where spacetime itself is subtly denser or more warped than elsewhere. Picture kneading dough and leaving behind a hidden pocket of extra flour. As the universe expanded, that unevenness could have created long-range gravitational tides, pulling matter toward it like a slow-motion whirlpool. Critics argue this theory stretches quantum mechanics to its breaking point. Quantum effects typically operate at scales 1 trillion times smaller than individual atoms, making their influence over galaxy-spanning distances seem improbable. But here's where dark flow gets strange. Quantum entanglement, the eerie phenomenon where particles instantly influence each other across vast distances, suggests the subatomic world might not play by our intuitive rules. If entangled particles can defy classical physics, could entangled spacetime have done the same in the universe's first moments? Some theorists speculate that a primordial quantum event, something akin to a cosmic scale entanglement, might have imprinted a directional bias on the infant universe, a whisper of asymmetry that snowballed into dark flow's colossal current. The challenge lies in testing these ideas. Quantum fluctuations from the Big Bang are frozen into the cosmic microwave background as faint temperature variations, but detecting specific anomalies linked to dark flow would require precision beyond our current tools. Future experiments like next-generation gravitational wave detectors or ultra-sensitive CMB mappers might one day spot the telltale signatures, subtle twists in spacetime's geometry or patterns in the CMB that betray a quantum origin. Until then, the theory remains a tantalizing what-if, a bridge between the universe's smallest quirks and its largest mysteries. What makes this hypothesis so compelling is its audacity. It dares to connect the dots between two seemingly unrelated realms, the chaotic frenzy of quantum physics and the stately drift of galaxy clusters. If correct, it would mean dark flow isn't just a cosmic oddity. It's a fossil from the universe's first trillionth of a second, a relic of quantum mechanics writ large across the heavens. And that realization would rewrite not just our understanding of gravity, but of reality itself. Einstein showed us that massive objects don't just sit in space-time. They bend it, warping the very fabric of reality around them. Now picture dark flow's scale, entire galaxy clusters, each weighing a quadrillion suns, all streaming in unison across billions of light years. If a single planet can slow time near its surface, what might this coordinated cosmic march do to space-time itself? The math gets dizzying fast. Some theorists speculate these vast movements could create faint gravitational wakes, like ripples in a pond, except instead of water, they'd be bending time's flow in ways we can't yet detect. Consider the strangest possibility. If dark flow's source lies beyond our observable universe, its pull might be stretching space-time like taffy, creating subtle gradients in how time passes across different regions. Near the flow's path, clocks might tick infinitesimally slower, not enough for humans to notice, but enough for precise instruments to potentially measure one day. It's like standing near a waterfall. The closer you get, the louder the rush, the more it drowns out other sounds. In this case, the sound is time itself, distorted by gravity's relentless current. Of course, this remains speculative. There's no direct evidence dark flow warps time. But the principle comes straight from general relativity. When the Voyager probes flew past Jupiter in the 1970s, their onboard clocks slowed by microseconds due to the planet's gravity. Scale that up to galaxy clusters moving at 1,000 kilometers per second, and the cumulative effect could, in theory, create localized wrinkles in spacetime's fabric. The weirdest part, this wouldn't be a one-time distortion. As dark flow continues dragging matter across the cosmos, these spacetime bends might propagate like seismic waves, echoing through the universe long after the clusters have moved on. Critics counter that the effect would be vanishingly small, lost in the noise of cosmic expansion, yet that hasn't stopped daring ideas from emerging. One radical hypothesis suggests dark flow could be winding up space-time in certain regions, creating vortices where time loops back on itself. Not quite time travel, but a cosmic version of a whirlpool where cause and effect might get tangled. Others propose these distortions could explain mysterious anomalies like fast radio bursts or cosmic voids, acting as lenses that magnify or distort signals from the early universe. The truth is, we don't have instruments sensitive enough to test these ideas yet, but future telescopes designed to measure gravitational waves with picosecond precision might one day catch space-time shuddering under dark flow's influence. Until then, it's a haunting thought that the universe's largest motions might be quietly twisting time itself, leaving footprints too subtle for us to see, but not too subtle to unravel reality's deepest secrets. Black holes are the universe's ultimate gravitational powerhouses, capable of bending space-time so severely that not even light can escape their pull. At the centers of most galaxies, supermassive black holes lurk like cosmic anchors, weighing millions or even billions of times more than our Sun. With such immense gravity, it's tempting to wonder, could these behemoths be behind dark flow's mysterious tug? At first glance, the idea makes sense. When black holes merge, they unleash gravitational waves powerful enough to ripple across the cosmos. Could a cascade of such collisions, perhaps in some distant corner of the universe, be nudging galaxy clusters off course? The short answer is no, at least not at the scales we're seeing. While black holes are undeniably strong, their influence drops off sharply with distance. Even the mightiest supermassive black hole's gravity peters out long before reaching the billions of light years spanned by dark flow. It's like trying to move a cruise ship by blowing on it through a straw. No matter how hard you puff, the effect is negligible. Simulations confirm this. When scientists modeled the combined pull of every known black hole in the observable universe, their cumulative effect couldn't explain the coordinated motion of galaxy clusters. There's another wrinkle. Black holes aren't distributed evenly, they're scattered randomly across galaxies. If they were driving dark flow, we'd expect galaxy clusters to show uneven motions, pulled toward regions with more black holes. Instead, the flow is eerily uniform, as if guided by a single, unseen hand. Even the most ambitious black hole mergers, like the record-shattering collision detected by gravitational wave observatories in 2019, don't come close to the energy needed to alter the motion of entire galaxy clusters. That doesn't mean black holes are irrelevant to the mystery. Some theorists speculate that primordial black holes, hypothetical relics from the universe's first seconds, could play a role. Unlike their modern counterparts, these ancient black holes might weigh as much as entire galaxies and could lurk unseen in intergalactic space. If they exist, their combined gravity might create subtle currents in the cosmic web, amplifying dark flow's signal. Others wonder if supermassive black holes could be markers rather than causes, their motions betraying the influence of whatever's truly pulling the strings. For now, though, the verdict is clear. As fascinating as black holes are, they're not the architects of dark flow. Their gravity is too localized, their distribution too patchy to account for the phenomenon's vast scale and precision. That leaves us with a humbling realization. Whatever's tugging at the universe, it operates on a level beyond even the most extreme objects we've discovered. Black holes may rule their galactic domains, but dark flow's puppet master reigns over something far larger, a shadowy realm where the rules of gravity as we know them might not even apply. Just when cosmologists thought dark flow couldn't get any stranger, another anomaly emerged, one that seems to point in the exact same direction. Scientists call it the axis of evil, a name worthy of a cosmic thriller. Discovered in the cosmic microwave background, this peculiar alignment isn't some random fluctuation. It's a pattern of temperature variations that stretch across the sky like a ghostly equator, all strangely oriented toward the same region dark flow is tugging. The odds of this happening by chance, less than 1 in 1,000. It's as if the universe left a hidden arrow in its oldest light, pointing to something we can't see. The axis of evil gets its ominous nickname from how thoroughly it upends expectations. The cosmic microwave background should look like a random scatter of hot and cold spots, a snapshot of quantum noise frozen in time. Instead, researchers found these variations lining up along a specific axis, almost as if the early universe were spinning like a top. That alone would be bizarre, but the real shock came when they plotted dark flow's direction. Both anomalies point toward the same patch of sky near the constellations Centaurus and Hydra. Two cosmic mysteries, one eerie alignment. What makes this connection so unsettling is what it implies about the universe's structure. The cosmological principle, the idea that the cosmos has no preferred direction, crumbles if both the CMB and galaxy clusters betray a shared bias. Imagine tossing confetti into the air, only to watch every piece drift not just downward but slightly northeast. That's the level of defiance we're seeing. Some theorists argue this could mean the Big Bang wasn't perfectly symmetrical, that some primordial quirk imprinted a directional preference on spacetime itself. Others wonder if we're seeing the gravitational shadow of something outside our universe, warping both the CMB and galaxy motions in one concerted pull. The most tantalizing clue lies in the timing. The cosmic microwave background dates back to just 380,000 years after the Big Bang, while dark flow affects galaxies billions of years later. If both trace back to the same cause, it would mean this mysterious influence has been shaping the universe since its infancy, a slow, relentless current guiding everything from the first atoms to the largest superclusters. Picture a river carving a canyon over eons. Only here, the river is gravity itself, and the canyon is the entire cosmos. Skeptics aren't convinced. They argue the axis of evil could be an illusion, a fluke of how we process CMB data, or even contamination from our own Milky Way's motion. But with each new analysis, from Planck's meticulous maps to simulations of the early universe, the signal refuses to vanish. It lingers like a whisper from the dark, hinting that these two anomalies might be pieces of the same puzzle. Whether that puzzle reveals a flaw in our models, a fingerprint from beyond our horizon, or something even stranger remains to be seen. One thing's certain: when the universe points at something twice, it's time to pay attention. The debate over dark flow's statistical significance isn't just academic nitpicking. It strikes at the heart of how science separates cosmic truths from cosmic coincidences. To understand why some researchers remain skeptical, picture a courtroom where the universe is the defendant, and dark flow's existence hangs on a single piece of evidence, a faint signal buried in the noise of the cosmic microwave background. Prosecutors, scientists who champion the phenomenon argue the signal is too consistent, too widespread to be random. The defense, a chorus of statisticians pointing out that even random data can appear meaningful if you slice it the right way. Here's where it gets technical. In cosmology, a discovery typically needs a 5 sigma confidence level to be taken seriously, meaning there's less than a 1 in 3.5 million chance the result is a fluke. Dark flow's initial detection hovered around 3 sigma, a threshold that translates to roughly a 1 in 750 chance of being wrong. That might sound impressive, but in a field where anomalies often vanish under sharper scrutiny, it's not enough to declare case closed. It's like hearing a faint whisper in a crowded room. You might think you caught your name, but without louder repetition, you'd never bet your life on it. Critics highlight another wrinkle, the look elsewhere effect. When you scan the cosmos for anomalies, the sheer volume of data guarantees some false positives will emerge purely by chance. Imagine rolling a die 1,000,000 times. You'd expect a handful of improbable streaks, like 26s in a row, even with a fair die. Dark flow's detractors argue it could be one of those streaks, a pattern that seems meaningful until you account for how many other patterns were ignored along the way. Even the alignment with the axis of evil, as eerie as it is, might just be a cosmic roll of the dice, but proponents counter with a compelling point. Dark flow isn't just one anomaly, it's a network of them. The coordinated motion of galaxy clusters, the CMB tilt, even peculiar velocities in supernova surveys all seem to point in the same direction. Individually, each piece might be shaky, but together they form a case that's harder to dismiss. It's like finding a suspect's fingerprints at a crime scene, their hair on the victim, and their face on security footage. Any one piece could be contamination or coincidence, but the cumulative weight starts to feel like more than luck. The stakes couldn't be higher. If dark flow is real, it upends cosmology's rulebook. If it's statistical noise, it's a cautionary tale about how even the best scientists can be fooled by randomness. Future telescopes like Euclid or the Vera Rubin Observatory might settle the debate, but for now, dark flow lingers in that frustrating gray zone, too intriguing to ignore, too uncertain to cement. And that's exactly where the most revolutionary discoveries often hide, on the edge of proof, teasing us with glimpses of a universe far stranger than we dared to dream. Cosmic inflation, the theory that the universe ballooned exponentially in its first fraction of a second, might hold the key to dark flow's origin. Picture the infant universe as a balloon inflating faster than light itself, stretching quantum fluctuations into cosmic-scale ripples that seeded galaxies and superclusters. But what if this hyper-expansion didn't just shape the universe we see? What if it also left behind gravitational echoes, subtle asymmetries now tugging at galaxy clusters like invisible strings? The math is tantalizing. Inflation predicts that spacetime should have stretched nearly perfectly smooth, leaving the cosmos homogeneous in all directions. Yet dark flow's coordinated motion hints at a primordial wrinkle, a slight unevenness in that expansion, like a crease in otherwise flawless fabric. Some theorists suggest this could trace back to inflation's abrupt end. When the exponential expansion stopped, the transition might have been slightly lopsided, creating a directional preference frozen into spacetime itself. Imagine blowing up a balloon with a weak spot. As it inflates, that flaw wouldn't vanish. it would stretch into a subtle gradient, influencing how the entire surface expands. There's a wilder possibility. Inflation didn't happen just once. In the multiverse scenario, our universe might be one bubble among countless others, each inflating independently. If neighboring bubbles brushed against ours during their expansion, the collision could have imprinted a gravitational asymmetry, a cosmic bruise that now manifests as dark flow. Think of it like bumping a spinning top. The nudge might seem insignificant at first, but over eons it sends the top veering in a new direction. Similarly, an ancient collision could have set galaxy clusters drifting on a path we're only now detecting. Critics argue inflation's predictions are too flexible. It can explain almost any observation after the fact, but here's where dark flow offers a rare test. If inflation truly left behind anisotropic imprints, future ultra-precise measurements of the cosmic microwave background might uncover telltale patterns, swirls in the polarization of ancient light or temperature variations aligned with the flow's direction. These wouldn't just confirm dark flow's cosmic roots, they'd reveal inflation's final moments in unprecedented detail, like finding fingerprints on a light switch from the instant the universe turned on. The stakes go beyond theory. If inflation carved dark flow's path, it means the universe's first trillionth of a second didn't just create space, it set in motion a gravitational tide still felt billions of years later. Every galaxy cluster caught in this current is essentially surfing a wave launched before stars even existed. That's the power of cosmic inflation, an event so brief, so unfathomably distant, that its ripples might still be guiding the cosmos today. And if we're right, dark flow isn't just a mystery, it's a message from the dawn of time, written in gravity's own hand. Dark flow's enigmatic pull hasn't just captivated scientists, it's ignited the imaginations of storytellers, weaving its way into science fiction as a symbol of the universe's untamed mysteries. In novels like Alastair Reynolds' House of Suns, the phenomenon is reimagined as a cosmic river, a literal current in space-time that ancient civilizations harnessed to navigate between galaxies. Films and TV shows, too, have latched onto its eerie potential. An episode of Doctor Who hinted at a gravity well beyond the observable universe, dragging entire civilizations toward an unseen abyss, a clear nod to dark flow's real-life controversy. These portrayals often amplify the science into something more visceral, a threat, a pathway, or even a sentient force lurking in the void. What makes dark flow so irresistible to fiction is the same thing that baffles physicists. It suggests a universe far stranger than we thought. Video games like Destiny flirt with the idea, casting it as the influence of the darkness, an antagonistic force seeping into reality from beyond the cosmic horizon. Even blockbusters like Interstellar, while never naming dark flow directly, echo its themes with their portrayal of gravitational anomalies and hidden dimensions. The phenomenon's real-life ambiguity gives creators license to spin wild narratives, blurring the line between cutting-edge science and speculative myth. But the most fascinating adaptations aren't the ones that turn dark flow into a weapon or monster. They're the stories that wrestle with its philosophical weight. In Liu Cixin's Remembrance of Earth's Past trilogy, a similar cosmic drift becomes evidence of a universe locked in existential warfare, where hidden civilizations manipulate gravity itself to survive. Here, dark flow isn't just a plot device, it's a metaphor for humanity's fragile grasp on reality. These tales tap into a deeper unease. If the universe isn't expanding evenly, if invisible forces tug at us from beyond the known, what else might be out there, unseen and unimaginable? Yet for all its fictional flair, dark flow's real power lies in how it mirrors our own curiosity. Sci-fi didn't invent the concept of hidden cosmic forces, it merely amplified what astronomers already suspect. That tension between known and unknown, between data and speculation, is what keeps both scientists and storytellers hooked. Whether it's a gateway to parallel worlds in a Netflix series or the subject of a tense debate in a lecture hall, dark flow reminds us that the universe's greatest mysteries don't just belong to science, they belong to anyone daring enough to look up and wonder. Here's the humbling truth. We might be trying to solve dark flow's mystery with the equivalent of a candle in a cavern. Our current telescopes, as advanced as they are, still have blind spots wider than the imagination. Picture standing on a beach at night, straining to see a ship's light on the horizon. Even with binoculars, the glare of nearby city lights, the haze of atmosphere, and the sheer distance could hide critical details. That's essentially our predicament with dark flow. The phenomenon points toward the cosmic horizon, a boundary beyond which light hasn't had time to reach us since the Big Bang. If the source lies in that unreachable darkness, no amount of squinting through today's instruments will reveal it. Take the James Webb Space Telescope, humanity's most powerful eye on the cosmos. While it can peer back to the universe's first galaxies, its vision still stops at the edge of the observable universe, the ultimate "you can't go past this point" sign. Dark flow's puppeteer, if it exists, might be lurking just beyond that line, tugging strings we can't see. It's like hearing whispers through a wall and realizing the conversation you're trying to eavesdrop on is happening in a room with no door. This isn't just a technological hurdle, it's a fundamental limit imposed by the speed of light and the universe's expansion. Even if we launched a telescope today with infinite sensitivity, regions beyond the cosmic horizon are drifting away faster than light can cross the gap. Their light will never reach us, no matter how long we wait. That means some mysteries might remain forever out of reach, their answers receding into the dark like a ship sailing over the edge of the world. Yet there's hope on the horizon. Future observatories like the Laser Interferometer Space Antenna or the Square Kilometer Array won't just push boundaries, they'll redefine them. These instruments could detect gravitational waves from collisions in the unobservable universe or map the large-scale structure of space-time with unprecedented precision. Imagine having a microphone sensitive enough to hear a pin drop in a thunderstorm. These tools might pick up the gravitational echoes of dark flow's source, even if we can't see it directly. Until then, dark flow stands as a reminder of how much lies beyond our grasp. Science thrives on questions, not just answers, and this might be one of those rare enigmas that lingers for generations, daring us to build better tools, ask sharper questions, and stay humble in the face of the cosmos' vast, untold stories. Dark flow doesn't just defy the laws of physics, it unravels something deeper, our cosmic certainty. For centuries, humanity has placed itself at the center of understanding, crafting models of the universe where everything obeys predictable rules, where the edges of reality are defined by what we can see and measure. But here's the unsettling truth dark flow whispers to us: we might not even be on the map. The sheer scale of this phenomenon suggests our observable universe, with its billions of galaxies, could be just a speck in something far grander, an unseen superstructure whose gravity tugs at us like a hidden puppeteer. Think of it like standing in a dense fog, convinced the few feet you can see around you are the entirety of existence. Then, one day, the wind shifts just enough to reveal shadowy outlines of towering mountains beyond the mist. That's what dark flow does to cosmology. It hints at mountains, not just unknown objects, but entire landscapes of reality lying beyond our perception, shaping the cosmos in ways we're only beginning to sense. Philosophers once debated whether Earth was the center of the universe. Today, we're forced to ask if the universe itself has a center, or if we're floating in the backwaters of something incomprehensibly vaster. This isn't just about science, it's about identity. Every major cosmological discovery has nudged humanity further from the spotlight. Copernicus exiled us from the center of the solar system. Hubble revealed our galaxy was one of countless others. Now, dark flow threatens to dethrone even the observable universe, suggesting we're not the main event but a side effect of forces playing out on scales we can't access. It's humbling, almost existentially dizzying, to consider that the sum total of everything we'll ever see, every star, every planet, every black hole, might be a mere eddy in a river flowing toward something we'll never know. The most profound implication, dark flow blurs the line between science and metaphysics. If structures beyond our cosmic horizon can reach into our reality and rearrange its contents, what does that say about the nature of existence itself? Are the laws of physics as universal as we thought, or are they local bylaws applicable only to our little neighborhood? Some theorists argue this could be the first tangible evidence of a multiverse, a reality where our universe is just one page in an infinite book. Others see echoes of ancient philosophical questions about whether the cosmos has an inherent direction, a purpose, or if we're simply caught in a current we don't understand. Yet there's a strange solace in this uncertainty. Dark flow doesn't diminish humanity's quest for knowledge, it expands it. Every unanswered question is an invitation to look deeper, to build better tools to stay curious. The universe isn't obligated to make sense to us, and yet here we are, piecing together clues from the faintest whispers of light and gravity. That's the real gift of dark flow, not answers, but the thrilling realization that the cosmos still has secrets left to tell, and that we're just beginning to learn how to listen. If dark flow is truly the cosmic tug-of-war it appears to be, could it one day rewrite the universe's final chapter? Cosmologists have long debated how the cosmos will end, whether it'll fade into cold oblivion in a big freeze, tear itself apart in a big rip, or collapse back into a singularity. But dark flow introduces a wild card. What if the universe's fate isn't just determined by dark energy's push or gravity's pull, but by something outside our reality, steering everything toward an unseen destiny? Picture the universe as a raft drifting down a river. Dark energy, the force accelerating cosmic expansion, is like the current speeding the raft forward. But dark flow, that's a hidden whirlpool downstream, pulling the raft sideways toward an uncharted bend. If this metaphor holds, the universe's demise might not be a slow fade or violent rupture, but a collision course with something unimaginable. Some theorists speculate that dark flow's source could be a neighboring universe in a higher dimensional space, inching closer as space-time stretches. Given enough time, trillions of years perhaps, that gravitational nudge might become a catastrophic drag, warping our universe like taffy until it merges with another. The numbers are staggering. If dark flow's pull persists, it could eventually override dark energy's expansion in localized regions, creating cosmic tidal zones where galaxy clusters are shredded by competing forces. Alternatively, if the flow stems from a pre-Big Bang defect in spacetime, it might unravel the universe from the edges inward like a sweater snagged on a nail. This wouldn't be the symmetrical big crunch of classic cosmology, but an asymmetrical unraveling, one side of the cosmos collapsing while the other expands into nothingness. Yet the most haunting possibility is that dark flow is a countdown clock we're only now noticing. If it's evidence of a multiverse, our universe might be destined to collide with another, not in a fiery cataclysm, but in a slow-motion gravitational embrace. Simulations of brain cosmology where universes float like sheets in higher dimensions show such collisions could reboot reality itself, triggering a new Big Bang. In this scenario, dark flow isn't just influencing the universe's fate. It's the first whisper of a cycle we're doomed or blessed to repeat. Of course, these ideas hover at the edge of speculation. Dark flow's signal remains faint, and its long-term effects depend on variables we can't yet measure. But that's what makes it so thrilling. For the first time, we're not just theorizing about the universe's end based on internal forces. We're peering beyond the curtain, wondering if the greatest threat or salvation lies outside our cosmic horizon. Whether it's a ripple from another reality or a flaw in the fabric of space-time, one thing's clear: the universe's finale might be far stranger than we ever dreamed. Science thrives on verification on different teams, using different tools, all converging on the same truth. Yet with dark flow, that consensus remains frustratingly out of reach. Independent astronomers have spent years poring over data from telescopes like Planck and the Atacama Cosmology Telescope, searching for confirmation of galaxy clusters' coordinated motion. Some studies claim to detect the signal, replicating the original findings with painstaking precision. Others return empty-handed, their instruments silent. The disparity isn't due to sloppy work. It's a reflection of how fiendishly difficult it is to measure such subtle motions across the unimaginable vastness of space. Take one pivotal study from 2014, where a team at the University of California analyzed over 900 galaxy clusters using Planck data. Their results, a tentative but tantalizing match with earlier dark flow measurements, showing clusters drifting at nearly 700 kilometers per second toward the same mysterious point. But then came the rebuttals. Critics highlighted how foreground noise, interference from dust in our own Milky Way, or subtle calibration errors could mimic the signal. It's like trying to hear a whisper in a windstorm. Even the slightest distortion can muddy the message. The plot thickened when the Dark Energy Survey, a completely independent project mapping millions of galaxies, failed to consistently replicate the effect. Their supercomputer simulations suggested galaxy motions could be explained by known structures, superclusters, and voids without invoking any exotic pull from beyond the universe. Yet intriguingly, their data didn't disprove dark flow either. It merely showed the signal was weaker than expected, like a fading echo. This left scientists grappling with a paradox. If dark flow is real, why does it flicker in and out of detection? Part of the challenge lies in the cosmic microwave background itself. The CMB is both a treasure trove and a hall of mirrors, its pristine light warped by everything it passes: galaxies, gas clouds, even the motion of our solar system. Isolating dark flow's signature requires untangling all these influences, a task akin to identifying a single voice in a thunderous choir. Teams using different methods, some focusing on galaxy cluster velocities, others on CMB distortions, naturally get slightly different results, like witnesses describing the same event from different angles. The most promising path forward may come from combining datasets in ways no single telescope can achieve. Imagine stitching together observations from infrared surveys, X-ray observatories, and gravitational lensing maps into a unified cosmic motion picture. Early attempts like the 2022 cross-analysis of Planck and ACD data show glimmers of promise, hints of a large-scale flow, though still shy of definitive proof. Until a new generation of telescopes delivers unequivocal evidence, dark flow will remain in limbo, too compelling to dismiss, too elusive to confirm. What's striking isn't just the scientific disagreement, it's what it reveals about the messy frontier of discovery. Dark flow isn't a clean-cut anomaly that neatly confirms or refutes our models. It's a shadow at the edge of perception, shifting shape with every attempt to pin it down. And that ambiguity, frustrating as it is, might be the most honest reflection of how science unfolds, not in eureka moments, but in decades of scrutiny, debate, and the slow unraveling of a universe that keeps its deepest secrets closely guarded. Dark flow leaves us staring into the cosmic abyss, confronting questions so profound they unravel the very fabric of modern cosmology. At the heart of the mystery lies its source. What colossal force could defy the universe's expansion, dragging galaxies across billions of light-years like leaves caught in a hurricane? All known physics suggests such a pull should weaken with distance, yet dark flow's grip remains unshaken, hinting at something beyond our observable horizon. Could it be an unfathomably massive structure, a gravitational echo from before the Big Bang, or even the pull of another universe entirely? Each possibility bends our understanding of reality, revealing how little we truly know about the cosmos. Equally baffling is dark flow's reach. Why does it stretch precisely 3 billion light-years, the limit of what we can observe before the signal vanishes? Is that boundary arbitrary, a quirk of our observational tools, or does it mark the edge of our universe's influence, beyond which another reality takes over? The alignment with the axis of evil deepens the intrigue, as if the universe itself is pointing toward a hidden focal point. A cosmic X marks the spot, with no treasure map to follow. This isn't just a gap in our knowledge, it's a chasm, forcing us to question whether the universe is even playing by the rules we've written. Perhaps the most unsettling question isn't about what dark flow is, but whether we'll ever solve it. The phenomenon teases us from the edge of detectability, its signal flickering in and out of focus like a distant radio station. Even with telescopes like Euclid and the Vera Rubin Observatory set to scan the skies, the culprit may forever lie beyond our cosmic horizon, forever unseen. Some mysteries refuse to yield, not because science fails, but because the universe keeps its deepest secrets locked away. Dark flow might be one of them, a cosmic whisper we're destined to chase without ever catching. Yet therein lies its magic. The greatest discoveries often begin with questions that refuse neat answers. Dark flow doesn't just challenge our models, it dares us to dream bigger, to imagine realities where gravity leaks between dimensions, where time bends under unseen weights, where the universe isn't alone. Whether solved or eternal, this enigma reminds us that the cosmos is far stranger, far wilder than we ever dared to suspect, and that's the most thrilling mystery of all. Dark flow isn't just another cosmic oddity, it's a revolution in how we see the universe. Over these 30 facts, we've peeled back layers of a mystery that defies the very foundations of cosmology. From the baffling alignment of galaxy clusters racing toward an invisible horizon, to the eerie whispers in the cosmic microwave background, dark flow forces us to confront a universe far stranger than we imagined. It challenges the cosmological principle, whispers of realms beyond our observable cosmos, and even hints that our reality might be just one thread in a vast multiversal tapestry. This isn't just about gravity or motion, it's about rewriting the story of everything. Think about what we've uncovered: vast supervoids that push matter like cosmic repellers, the Great Attractor's gravitational dance, and the spine-chilling axis of evil, all seemingly connected to dark flow's relentless pull. We've grappled with theories ranging from quantum echoes of the Big Bang to the gravitational fingerprints of other universes. Each clue has been a breadcrumb leading us deeper into the unknown, forcing us to question whether the universe is uniform, infinite, or even alone. The sheer audacity of these ideas that something beyond our cosmic horizon could reach in and rearrange reality is both humbling and electrifying. But here's the exhilarating part: dark flow isn't a dead end. It's an invitation. Every unsolved mystery is a door waiting to be kicked open, and this one's no different. With telescopes like Euclid and the Vera Rubin Observatory scanning the skies and theories evolving faster than ever, we're on the brink of breakthroughs that could reshape physics itself. Whether dark flow is confirmed or debunked, its legacy is already cemented. It's shown us how much we don't know and how thrilling that ignorance can be. So what do you think is out there? A parallel universe, a cosmic defect from the dawn of time, or something no one's even dreamed up yet? The universe is a conversation, and dark flow is its most provocative question. Hit the comments with your wildest theories, and if you're hungry for more deep dives into the cosmos' greatest enigmas, make sure to subscribe. The universe isn't done surprising us, and neither are we.